Hi, my name is Lowell Lobo, and I'm a graduate student in University of Maryland, and I will now be presenting my work in implementing a paper that is the nonlinear model predictive control for growth robots. So before we start in the paper, let's first try to understand what a growth robot is. So a growth robot or a continuum robot is a type of robot which has no rigid links and they look very continuous in their appearance. So on the slide, there are two images just to show how a growth or a continuum robot looks like. Now, a growth or continuum robot can be expressed in four different ways or four different robot parameters. The first one is the S value, or which is known as the arc length of the robot. The next one is the phi value, which is the rotation of the robot's end effector with respect to the x-axis. Then another one is the curvature k of the arc. And finally, we have theta, which is the elevation angle from the xy plane all the way up to the end effector position. Now, going back to the paper, let's start with the derivation process of how we get the design. We have three steps over here. So first we get the modeling, as in trying to find the equations of our robot model. And then we take those equations and try to bring them into the state space representation. And finally, we design our nonlinear model predictive control. So let's start with modeling. First, we start with the position kinematics. Now, in the paper chosen, the position kinematics were actually just directly taken as a citation from some other paper. So personally, I don't know properly about what method was used in derivation of the position kinematics, but there are two ways to do this. One is geometrically using transformation matrices, or the other way is using DH parameters. So I use the geometric way of finding the position kinematics. Over here in the equation, you see the values of x, y, and z written in the with relation to the robot parameters s, which is the arc length, phi is that rotation angle with respect to the x-axis, and theta, which is the elevation angle of the end effector. Now we have position kinematics of the end effector position. From this, we can get the velocity kinematics. And the Jacobian is found in such a way that it is a partial differentiation between the end effector position and the robot parameters. So over here, P is basically the end effector position, X, Y, Z. And the robot parameters chosen over here is S, which is the arc length, theta, the elevation angle, and phi, which is that rotation along the z-axis with respect and the angle with respect to the x-axis. Now, when we find the Jacobian, we can just directly input the velocity kinematic equation as since P is considered our end effector position, our equation becomes P dot equals J, which is a Jacobian, times some value, let's say it's Q dot for now. So it'll be in the form of the velocity of the end effector is equal to the Jacobian times the velocity of the robot parameters. Next, let's go to the state space model. But before we actually try to derive our state variables, we need to take into consideration the fact that this is a growth robot. And when a growth robot is classified as something that only grows but never shrinks. So this growth is considered irreversible. Also, another aspect is that the growth should be slow. If the growth is too fast, it can lead to like the material properties becoming needing to be like the material properties of the robot need to be strong to withstand such a fast growth. Therefore, it's always considered best to have slow growth. So the two conditions, one is irreversible growth and slow growth. Now, growth as a parameter can only really be shown properly using the robot parameters. And the most important parameter is the S value or the arc length. So the arc length would be able to show us how big the robot is. So if ever the S value or the arc length decreases, that just shows that the robot shrinks. Now, taking into account our velocity kinematics equation, which is just the velocity of the end effector, is directly related to the velocity of the robot parameters. We could just directly take the state space variables as x, y, z being the end effector position, and we would get some state space equation. But that doesn't really allow us to capture that irreversible growth of the robot. Therefore, we add the robot parameters also as part of our state space equation. So our state variables now become x, y, z, which is the end effector position, and s, theta, and phi, which is our robot parameters. So then let's say that's some vector x. So x dot would now be the velocity of the end effectors and the velocity of the robot parameters. Now we know that the relation between the velocity of the end effectors is a Jacobian times the velocity of the robot parameters, and the velocity of the robot parameters is just directly related to itself. So then we can get this state space equation in the form where we have the x x dot is equal to the Jacobian and a matrix basically, which the first half of the matrix is our Jacobian. The next half is an identity matrix and directly related to some vector q dot, where q dot is the velocity of the robot parameters. Now this looks like the form of x dot is equal to b u. Since our states x, y, z, s, theta, and phi are not really there in the equation, so our matrix over here, J identity, will be considered our B matrix, and Q dot will be considered our U matrix, or the control input or control action. Now going to the nonlinear model predictive control design, we take a cost function. This cost function has been stated in the paper, and this is the exact same cost function, where over here it's written in the form of the error times some weight matrix, and the summation of the error time with some weights given, and the difference or the increment in the control action again with some weights given. The error is basically the current position minus the reference. And on this cost function, some constraints are put, especially because we were trying to look at that irreversible growth, and then some other robot parametric constraints like actuators to make sure that it can work in the environment. Also, another important aspect is that for nonlinear model predictive control, this design requires a discrete time linear model, but what we have is actually a continuous time. So if we know the previous state space equation. So we have to convert that state space equation into a discrete time linear format. So this is done through Euler discretization. Now going to the results of simulation, there were 4 main simulations that were conducted. And we will go through each of them to see how our simulation compares to the simulation in the paper. And then if there are any discrepancies, we'll try to give some reasons for why that is so. So starting with point stabilization. Over here, we have the image for the paper and the personal results. So comparing both, we can see that the X value in the personal result shoots up to 1, like immediately shoots up to 1 instead of having slow increments. And if we had to compare the time slot between 0 and 10, and then 10 and 20, it's almost as if they have been swapped. So where in the paper from 0 to 10, whatever happens is actually happening from 10 to 20 in the personal simulation. Then if you see towards the end, after the 50 seconds of the simulation time, instead of like the X and Y value and the S value in the paper, like the X and Y value goes upward, while the S value goes down in the paper simulation, but it's the opposite in our personal simulation. But otherwise, the graphs look very similar. Now, any discrepancies we would try to explain a little bit later in a separate section. In this section, we're just trying to look at the results and what we're inferring from these results. The second test that was done was obstacle avoidance, where an obstacle is placed in some 3D space and the robot tries to navigate around the obstacle. Now to do this, of course, another special constraint was added where the Euclidean distance between the object and the end effector position should always be greater than 0. Now, if we look at our simulation results for the paper, it just moves pretty fluidly and goes around it. And it's important to note that the robot in the paper evades the obstacle by going under the obstacle. But then in our personal simulation, again, we see that the Z value shoots up to 1, like almost immediately, and there's no slow increments. And the robot trajectory actually goes from above instead of going below. And now if you remember from the previous simulation, I can show you over here, Even over here in our person simulation, the the trajectory taken is actually the opposite in terms of whatever trajectory it's taking. So over here there must be some difference in the algorithmic design that makes it such that the robot's trajectory is taken to be the opposite. But all in all, it's the design successfully avoids the object. Next, looking at trajectory tracking, this over here is actually the unconstrained model where the constraints are not really put in place. Next, in the next slide, we will show the results with the constraints being put. We see that there is a good trajectory of the person simulation compared to the paper simulation. It's just that after the points 25 and all the way up to the end of the simulation, we see that there is a bad zero tracking error, especially in the Z value. Again, this will be explained later when about the discrepancies. Now, trajectory tracking, looking at a constraints model. Now over here, the paper results are very unclear, where normally logically thinking, it should be possible to actually go through the whole circle, but for some reason, the paper shows that the y value goes up to 0.5 and just cuts in between. No added information has been provided in the paper. It's just that this one image, so it's not really easy to infer. And then looking at our personal results, like according to logic, it does try to reach the reference trajectory, but it only follows the trajectory initially, and then towards the like in the middle, it just stops working completely. Again, discrepancies will come later. Then robustness analysis. In robustness analysis, some disturbance is added into the system. And then we are trying to look at different weight matrices that allow the system to stabilize at some specific point. So over here, the point given is just 111. We're trying to see how it stabilizes. Now, this robustness analysis actually helps us understand what's happening. Even like previously in our point stabilization, trajectory tracking, and object obstacle avoidance, like the reasons for why that's happening can somewhat be explained because of this robustness analysis. So if you see in our first simulation, we have given weight matrices. Everything is equal, but the weights are given more on the end effector positions rather than the robot parameters. And we see that again, the Z value just shoots up to 1. The Y value doesn't increment at all. And the X value starts off good. It hits the reference, but then just deviates. Looking at the second simulation, we see that the simulation results actually look pretty good, but again, the Z value just shoots up to 1 instead of slow incremental growth. But over here, we have given stronger weights on the X value and the Y value. And because of giving the stronger weights on X value and Y value, and not the Z value as compared to the first simulation, the X and Y value actually stay on their reference point. And over here, also especially important to note, this will come later, is that in our weight matrices for our robot parameters, which is R, or the control input, which is R, the second one is actually our theta value. The first one is our S value, which is the arc length. So we are given more weight or importance on to the arc length, and therefore it's showing a good result. Going next, again, another 2 simulations were done. Again, now the weight matrices were changed again a little bit. Disturbances again also were a little changed. And we see that again, in the first case, it's again, the Y value doesn't work at all. X value just shoots up very fast. But if we compare this, and remember from the previous case, although our diagonal matrix is the same as the previous simulation too, we see that our R matrix, which is our weights on the control action, are all equal. And this is actually the reason for why there's such a bad trajectory tracking, which we'll get to later. And looking at the second simulation shows a good result, where again, almost similar diagonal matrices, and but we see that the Z value just shoots up and then suddenly goes down and comes back up again, which is not really good for a slow incremental growth. Now we will try to explain some of the discrepancies. And mainly the discrepancies come from two reasons. One is the model design inaccuracy, and the second one is the algorithm implemented for our nonlinear model predictive control, which is multi-shooting. Let's start with the model design. So in the paper, it is not exactly provided what the model being used is. They just say that the Jacobian can be calculated analytically, and then you have to just find it. So the exact model is not being given. So when I tried to derive the model, the equations given over there for the z value, it's in the form of sine theta by theta, and then another term. And also important to note that every parameter in the Jacobian actually is divided by theta. So if all values are divided by theta, like just look at the sine theta by theta, for example. If theta is equal to 0, that's just undefined. In the same way, even for the second part, if theta is equal to 0, that's again just undefined. So over here, z is, and especially at the initial condition, because the paper takes the initial condition as theta equals 0, z is undefined at initial condition. And if you try to evade this problem by taking like a very small value of theta, like 0.0001, if we look at the second parameter of the z value, that actually doesn't reach 0. If we were to plug in the values for theta as a very small value, that it reaches like an incremental growth in value. And it's also important to note, as you can see in the graph being displayed, that second parameter is actually that what is being shown as undefined, and there's no convergence exactly between the points, especially when theta tends towards 0. So in this way, the model which has been personally derived doesn't really work for our scenario, especially when theta is very small value. So this can be, and this is why one of the reasons for why z always shoots up to 1. It's because in our initial condition, theta is always taken as a very small value. And so z just directly shoots up. And then because of this shooting up, the x and y values of the end effector position are not able to properly understand what's happening in the system. Also, it's important to note that having greater weights on the z value or the theta value would give to a more minimized value of theta, and that again leads to a bad model. In some way, the paper has reduced their model, but the information has not been provided, and therefore it's not really possible to understand what the exact model is to required is. And then we come to our multi-shooting algorithm. So over here, for the implementation, there are really two ways to do our implementation algorithmic wise. One is through single shooting. The second one is through multi-shooting. And for single shooting only takes into consideration the control inputs into our optimization, while multi-shooting takes all the state parameters and the control inputs part of the optimization. Now, in doing so, this actually adds more constraints on the system, but also makes sure that the reference tracking is better in the multi-shooting case. And the most important thing is the equation being shown over here, which is with the vector x k plus 1 minus xp k plus 1. What that equation basically means is that our current state or the next state, according to the prediction, should always be equal to our plant model's next state. And therefore, we see it's like the next state minus our plant's next state should be equal to 0. So in multi-shooting, we use all state variables. And if we see, especially from robustness analysis, and because of robustness analysis, we see that when you have higher weights on z value, it always tries to prioritize z increment all the way up to 1. And it also prioritizes the minimization of theta value, because in the relation being shown over here, when theta is very small, z just directly goes to 1. That just reduces the error immediately. And therefore, that's one of the reasons as to why there's an error in most of the simulation results. And this mainly comes because of the multi-shooting algorithm chosen over here. So in conclusion, a nonlinear model predictive control algorithm was designed with reference to the paper chosen and taking all the derivations from there. The results of simulations were compared, And we could see that the results vary quite a bit, but this is because of the lack of information. And the lack of information is especially in how the model has been reduced to make it work at cases where theta is very small or equal to zero. And also the the algorithm employed has not been provided, and especially because there are two different ways and both can give different results. Thank you very much.